Hmm. um, Welcome to my live broadcast, and I'm going to be going over some problems from my AP Stats class today that were to help my students get ready, for one of my students, to help you guys get ready for the test tomorrow. So what I'm going to do is go through the problems one by one and just kind of give a quick explanation of how and why the answer is the way it is. And then if you want to comment, you can comment. I think you can send comments. I've never actually live broadcast before, so I think you can do comments in the comment section, and then I can just reply back to that. So let's see. If I can find out how to get that. And then I'll get started in just a second. Okay, so I think there's a way to record this. I actually don't know how to get chat enabled, but I'll go ahead and get started anyway. So what I'll do is look at the multiple choice first. So I think in my class we left off at number 5. What I'm going to do is show you the problems here so you can kind of go along with me on this. And so let me go ahead and share those with you. Sorry guys, I just got to work out some bugs here, make sure everything's working all right. All right, here we go. All right, so what you should see here is you should see the problems that were that were given in the class today. So the first one here is that we left off, I think we left off at number 5. Investigators in agricultural research facility randomly assign equal numbers of chickens to be housed in 2 rooms. So we're looking at let me zoom in here so you guys can see this. All right, we're looking at a difference, okay, right? A 2-sample t-test. Okay, one-tail alternative. So one-tail alternative means that it's got to be a greater than or a less than, right? With a p-value of 0.2, now that's a pretty large p-value. Any p-value bigger than 0.05 is pretty large. So let's see which is true here. The chickens in the lighted room average 0.22 more eggs per day. Well, that's absolutely not true because it's not what the p-value says. The p-value is talking about the chance that this is going to happen simply by chance, right? There's a 22% chance that chickens housed in a lighted room produce more eggs. Again, that's not what it says. There's a 22% chance that there's really no difference in egg production. Again, that's not what it's saying. And there's a 22% chance another experiment will give the same results. That is probably the closest one. That's probably the closest one we're going to get. There's a 22% another experiment will give these same results. Now, simply by random selection, I probably would be a little bit more specific and say simply by random selection. Let's go down here. 5 is E. And like I said, you know, I would want to be much more specific on whether or not what we're talking about here is that there's a 22% chance another experiment will give the same results simply by random selection, right? Simply by chance this is going to happen. That's what the p-value states. Not that it's going to happen, but you know, it's just simply by chance it will happen. So this is going to be none of these, right? This problem here is a question about whether or not you understand the p-value. All right, want to know the mean winning score. We create a 95% confidence interval based on a t-distribution. This procedure was not appropriate. Why? We want to know the mean winning score at the US Open Golf Championship. Internet search gives us all the scores for the history of that tournament. Well, this is a, you know, if we have all the scores in the history of that tournament, that means we're going to end up with the population mean. We're going to know what the true mean is. And if we know what the true mean is, and we're doing, we really don't need to do inference on, well, we really are not going to do inference on the population. We don't do inference on the whole population data. What we're doing in inference is we're trying to see if a sample is going to give us information about the about how we compare or about the entire population as a whole. So, you know, we probably say that the population standard deviation is known because we know all the scores. What do we got here? Let's check. 6 is B. What did I say? I said D. Huh. What do you know? The entire, well, you know what? I should have read all of them. The entire population of scores was gathered, so there's no reason to do inference. That's exactly what I said, right? I just didn't read all of the questions. So I should have read all the possibilities first, but you can clearly see that that's what I said. We did the entire population. There's no reason to do inference if we know the whole thing, right? And also, creating a 95% confidence interval, we only create a confidence interval if we're trying to kind of guess what the true mean is. Well, if we know the true mean, why do we want to guess it, right? So that's just silly. Okay, so food inspectors need to estimate the level of contaminants in food products packaged at a certain factory. Initial tests were based on a small sample, but now the inspectors doubled the sample size for a follow-up test. The main purpose of a larger sample is to excuse my coughing. Decrease the standard deviation of the sampling model, reduce confounding due to other variables, reduce response bias, decrease the variability in the population, reduce non-response bias. So look, guys, this D is absolutely wrong, right? Decrease the variable in the population. We can't decrease the variability in the population. You know, the population is going to have variability that it has. We can't decrease it. We're taking a sample anyway. Bigger sample, that means we're going to shrink the variability. If we have a larger sample, the variability goes down. The measure of variability is standard deviation, which means that there's a decrease in standard deviation for the sampling distribution. So our answer here is A. Oops. So let's look at the next one. Based on data from two very large independent samples, two students tested a hypothesis about equality. Reject the null hypothesis. The other used a two-tailed test and failed to reject the null hypothesis. Which of these might have been their calculated value of t? So look, guys, we have a a problem here because, you know, if someone did this, you know, and right here we got 0.025, and here we got the same thing. Now, one-tailed is going to reject the null hypothesis, right? And then two-tailed, we add them together, it's going to be too high on the alpha level, so we're going to fail to reject the null hypothesis. So now we got to figure out which of these t values could that possibly have been. Now these data are based on two very large independent samples. So very large independent samples has me thinking that if we were to think about this like the normal model, we would, because you know, as the t as the sample size gets larger, the t model gets closer and closer to the normal model. So if I was thinking this as the normal model, anything above 2 standard deviations above the mean is going to be unusual, and we're going to end up rejecting the null hypothesis. So my guess here is that the t-score is probably going to be about 1.88. This seems like it's reasonable. It's close to 2, and it seems like if I had, you know, close to 2 here and I had 2 shaded regions, I'm going to end up failing to reject the null hypothesis. But 1 shaded region is still going to reject the null hypothesis. It's still going to be below an alpha level 0.05. There's no easy way to do this, guys. It's just kind of thinking about what's going on here. Like there's no formula that I would use. So number 9, there's kind of a crazy formula for this, which I didn't go over in my class. It looks like this. It's S pooled squared is equal to S1 squared times the degrees of freedom for 1 plus S, let me zoom in here so you can see what I'm doing, plus S2 squared degrees of freedom for 2 divided by the degrees of freedom for 1 plus the degrees of freedom for 2. And you're thinking to yourself, Mr. Myers, come on, you didn't give this to us in class. Do we have to memorize that? No, guys, you don't have to memorize this. If this is a question on the test tomorrow, I will write this up on the board for you so that you can use that. But basically, you're just going to plug these values in. All right, boom, boom. And then once you get that, you're going to take the square root of both sides, obviously, to solve for SP. And that's going to give you the answer, which is 7.22. All right, so this is the formula here. I'll zoom in here. You can see that formula. Okay. And again, I'll give that to you in class, so you don't have to worry about that. All right, so let's look at number 10. You could win a $1,000 prize by tossing a coin in 1 of 2 games. To win game A, you must exactly get 50% heads. drinking some water here. To win game B, you must get 45 and 55. Although you choose the games at random, you get to decide whether you're going to toss 20 coins or you're going to toss 50 coins, the coin 20 times or 50 times. So how many do you choose depending on which game you play? Well, if I was playing these games, I would definitely choose to toss 50 for B. And the reason for that is because between 45 and 55, this is kind of like a confidence interval, right? And the law of large numbers states that as I increase the number of samples, I should get closer to the true proportion. Well, 45 and 55, we know the true mean should, or the true proportion should probably be around 50. So this gives me a plus or minus 5 margin of error to make as I increase my samples. So I'm definitely going to choose to do 50 tosses for game B. Now for game A, well, for game A, I have to get exactly 50. And to get exactly 50, it's actually harder to get exactly 50 with a higher sample size than it is with a smaller sample size. You know, because if I do 2 coins, 2 flips, right? Doom, doom, heads, tails, right? The probability of getting heads the first time is 1/2. The probability of getting heads or tails the second time is 1/2. We got 1/4. We got pretty much a 25% probability, theoretically, of getting 2 different things, which is exactly 50%, right? So, but once I keep putting more and more and more and more tosses in there, that probability is going to go down because I'm going to end up keeping them multiplied by half, by half, by half. So it's going to be harder to get exactly 50 when I increase that sample size. So what I'm going to probably do is choose 20 tosses for A. So my answer here would be D. Oh, that's the wrong thing. 20 tosses for A, 50 tosses for B. All right. So part of that you could just kind of think through. You don't even really have to do much there. And again, I'm going to go through these individually. If you feel like I don't need to listen to them do this, you can come back while I go through this, or just put me on mute until you get to a problem that you want to hear. It's okay with me. So family incomes, a government report on standard living says that family incomes nationwide are skewed to the right. Now, what this is telling me is that the population is skewed to the right with a mean of 33,400, not the sampling distribution, but the population. Now, we collect data from a random sample of 50 local families. Why is it okay to use these data for inference, even though the population is skewed? Remember that one of the assumptions and conditions is that the sampling distribution, our sample, is unimodal and symmetric, so we can use the normal model. Well, that's okay for our sample and the sampling distribution. It's not so we're doing inference. We're using the sample, not the population. So as long as, I want to be clear here, as long as the sample size is large enough, the law of large numbers will allow us to do inference on that sample. So I would say, let's see, I would say that since the sample size, that's not very good writing there, size is large enough, we can use it for inference. That's all that needs to happen, is that the sample size needs to be large enough, okay? All right, so let's look at the next one. The standard deviation of 50 incomes in our sample. And I would turn this to the side, guys, so it's easier to see, but for some reason my computer doesn't let me do that. The standard deviation of 50 incomes in our sample is 25,530. Specify the sampling model, shape, center, and spread. Okay, I turned it off. You can probably see my face now. So I don't know if chat's available. If chat is available to you, you can put in questions in the chat and I can see it on the side here, and let me know if you have any questions. Now, the reason I turn it off is because I'm going to go to my calculator because I need to do some calculations. So let me get my calculator out, and still want to screen share that, so you're looking at me, not my calculator. All right, this might be kind of crazy, but here it goes. Oh, look at that. Infinite. My Estes is infinite. Okay, take a look at this, guys. So, oh, this is that formula I was telling you about for that previous one. So here's what we're going to do. We know that we're talking about a standard deviation of 50 incomes in our sample. We're talking about means, right? So if we're talking about means, we're going to use a T model. So it says specify the sampling model. Our sampling model is the T model. The T model with, in this case, 49 degrees of freedom. But I need to find the center, which is easy. That's the population mean, 33,400. But I need to find the sampling distribution, or I'm sorry, the standard deviation of the sampling distribution. And in order to do that, I'm going to use my formula. Hopefully you can all see this. I'll make it bigger here. So I'm going to use the formula to find the standard deviation. I'm going to use S I'm going to use S, which is the standard deviation of the sampling distribution, divided by the square root of n. All right. So let's go and do that, and I'll do that in my calculator. So I know that the standard deviation is 25,530, and I want to divide that by the square root of 50. I'm put a decimal here just because I'm using the CAS, and I get 3,610. I'm just going to go ahead and round that up. Okay, 3,610. Okay, so I'm going to go back here. Not sure if you can see that. I'll make it bigger here. Oh, that didn't help. Okay, let's do this. Oh, look at that. My lovely face is back on the screen. All right. Okay, so here we are back at my problem. So I said this was going to be a T model with 49 degrees of freedom. The shape is going to be unimodal and symmetric. What else do I know? I know that the center is the mean, which was the population mean, 3,400. And the standard deviation is, what did we say it was? 3,610. All right. So remember, you got to use the sampling standard deviation, the sampling. So you got to use S over the square root of n. 25,530 over the square root of 50. All right. Okay, let's look at the next one. Again, I know I'm going through all these. It's going to take me probably another half an hour to get through some of this stuff, but you know, it is what it is. A sample of randomly chosen families produced. Now, it shouldn't take you this long. I'm going over them. It should take you, you know, half the time. This sample of randomly chosen family produced 90% confidence interval, local mean family income. Does this interval provide evidence that the family incomes are unusually high here? Guys, this is an easy one to explain because the population mean is 33,400, and that is clearly within our confidence interval. So does that provide enough evidence? Absolutely not. It does not provide enough evidence that they're unusually high, because the mean could be right in the middle, right? It could be exactly the same as the population. if we were, what we would be looking for is if these numbers were higher than that. My confidence interval was bigger than the population mean, then yeah, it would be unusually high, but it's not. So no, there is not enough evidence that incomes are high. Because the population mean is in our interval. Okay? Okay. So again, you need to make sure that if the confidence interval was greater than that, then of course, then we would say yes, there is enough evidence. Suppose we hope to improve our estimate by choosing a new sample. How many families must we survey to have 90% confidence of estimating the mean local family income within 2000? So what this is telling me is that this is my margin of error. Okay, my margin of error is T star with degrees of freedom. In this case, we don't know the degrees of freedom. S over square root of n. Now, so my margin of error is 2000. I don't know my degrees of freedom, so I'm not going to be able to find T star depending on my degrees of freedom. However, it is pretty big. 50 is a pretty big sample. So what I'm going to do is I'm going to actually use Z star. Okay, I'm going to use Z star to figure this one out. And S we know is 25,530 over square root of n is what we're looking for. So Z star for 90% confidence. Z star for 90% confidence is, let me look that up real quick. If you want to know how to do it, I'll show you right now. How's that? So if you want to know how I'm doing that, let's go to, that's weird. Okay, let's go to my entire screen here. Again, infinite maestas. Okay, so what I'm doing here is in my calculator menu, I'm going to go to menu, statistics, so that one, distributions, inverse T. Oops, I want inverse Z, sorry. Statistics, distributions, inverse normal. And my area is going to be, since I'm looking for a 90% confidence interval, my area is going to be 95. 1.64. Okay, so 1.64 times 25,530 over root n. Okay, so to solve this, I'm going to divide this. Well, actually, okay, hold on. Let's do a little algebra here. I'm going to multiply these two guys and then divide them over. So I'm going to have 2,000, and I'll make this bigger here so you can see my work. 2,000 divided by 1.644 times 25,530, 419. 71.3. Ooh, that's a big number. And then that's going to be equal to 1 over the square root of n. So then what I'm going to do is I'm going to invert and square. All right. So I'm going to have, let's put in parentheses. I hope you can still see my calculator. I think that's what I still have it on. 41971.3 over 2000 squared. 440 would be my new n. All right, so that's what I have for n. That would be the sample size. That's a huge sample size. Let's see if that's what they got in their answer here. Yeah, around 450, right? Depending on the critical value. So that's what we did, right? We got 450. Well, we got 440, which is basically what you really needed to do, right? 440. Okay. All right, so let's move on now. We did all these. We did number 12 in class, so I'm not going to go over number 12. Infinite maestas. Infinite maestas. Man, if I could only clone myself and be infinite, I tell you, I'd be a million gazillionaire. It's not a real number, but hey. Okay. Factory recently installed new population pollution control equipment. You can keep reading while I drink some water. Randomly timed measurement of sulfate levels were taken before and after. Ooh, before and after. Whoo, before and after. I already know before and after is probably going to be matched pairs. All right. So we're probably dealing with matched pairs. We believe the measurements of sulfate levels are normally distributed. Perfect. Write a complete conclusion about the effectiveness of these scrubbers based on the statistical software printout below. So guess what, folks? We actually don't need to do anything. We just need to look at what they got and deal with the the information. Well, I said it was going to be matched pairs, but they didn't do a matched pairs test. They did a 2-sample t-test. So since that's what they did, we're going to go with what they did. All right. So let's take a look at what they got. Zoom in on this box here so we can see this. So they have this set of data for C1, C2. They did a 2-sample t-test. The number of elements in C1 is 12. C2 is 10. And then they give us some information here. The mean, the standard deviation, the standard error, and so forth. They gave us a 95% confidence interval for mu1 minus mu2. Well, that seems interesting. That confidence interval is both positive. So we know that it's both positive. We're probably going to reject the null hypothesis, whatever that hypothesis may be. So here's our null hypothesis. That mu1 is equal to mu2 versus not equal. So this is telling us that our alternative hypothesis is mu1 not equal to mu2, right? And clearly, if they were equal, we would find a 0 in the confidence interval. We are furthermore, we see that the p-value is smaller than an alpha level of 0.05. Now, we weren't given the alpha level, but we'll assume that that's what it is. So we got a small p-value. So look, guys, we've got a confidence interval that clearly shows that 0 is not in the interval. We have a p-value that's small, which tells us that we're going to reject the null hypothesis. So let's let's state our conclusion in context. That's basically all we're doing is stating our conclusion. Okay? Since our p-value is small, there is sufficient evidence. I know I can't write. I'll show you the actual typed out version in just a second. That there is a difference in mean sulfate levels before and after using the scrubbers. It's a funny word, scrubbers. All right. Furthermore, we can even talk about the confidence interval, right? That the average sulfate level was between 1.2 points higher, 1.2 micrograms per cubic meter higher, and 5.38 micrograms per cubic meter higher after using the scrubbers than before using the scrubbers. That's pretty significant, guys. All right, that's pretty significant if I was this company. Let's look at the typed up answer for this so that you can see what that looks like. P is less than 0.05 is strong evidence that the scrubbers have changed the mean pollution level. We're 95% confident that the mean sulfate level has decreased between 1.2 and 5.38 micrograms per cubic meter. All right, which is kind of what we said here. I think I was saying it differently when I meant it the other way around, right? Yeah. See, I'm sorry, C1. So guys, C1 is going to be bigger than C2, right? Since these are positive, which means that C2 brought things down. It brought it down because this is going to be a smaller value than the original value, which means that the pollution went down by 1.2 micrograms to 5.3 micrograms. Right, so I was kind of reading that incorrectly. You got to make sure you read these guys right here, the mu1 and mu2, and know which one's bigger and which one's smaller. All right, blood pressure. So we got 14 and 15, and then I'm done. YouTube says I can take 8 hours. So, you know, if you guys really want, I could just like, you know, just crush it for 8 hours for AP stats. I don't think so. I need some sleep too. Researchers developing new drugs must be concerned about possible side effects. They must check a new medication for arthritis to be sure that it does not cause an unsafe increase in blood pressure. They measure the blood pressures of a group of 12 subjects and administer the drug and recheck the blood pressures 1 hour later. The drug will be approved for use unless there is evidence that the blood pressure has increased an average of more than 20 points. They will test the hypothesis using an alpha level of 0.05. Write appropriate hypothesis in words and symbols. Look, guys. I would say that mu difference equals 0. And the alternative hypothesis would be that mu difference is, you know, it all depends on how you put mu difference. We'll say it's greater than 0, but what we'll say is that mu difference is mu after minus mu before. And if I was doing this in words, I would say that the average blood pressure after using the drug minus the average blood pressure before using the drug will be the mean difference of the blood pressures. Okay? Oops. And I feel like that should be greater than 20. Yeah, that's what I thought. I want this greater than 20, guys. I think that makes sense. You know, I was thinking 0, but you know, it really does make sense that I want that difference. I want that difference to be if the after minus the before, if it increased, by more than 20, then we're in trouble, right? Because then there's evidence that the blood pressure is increased. And we don't want that to happen, right? Because if the blood pressure is increased, then we have some problems with the medication, and the medication is going to make people's blood pressure is going to increase, could possibly result into death. So we don't want that to happen, and it gives us a value to kind of gauge it upon. It's not asking if there's a difference. It's just it's asking if that difference is greater than 20. So we want to write our hypothesis like that. In this context, which do you consider to be more serious, a type 1 or type 2 error? Well, let's think about this. A type 2 error would be if the null hypothesis was type 2 error would be, let's go there. If the null hypothesis was true, no, the null hypothesis was false, and we failed to reject it, right? So, I'm sorry, the null hypothesis is true, but we reject it. So, what's going to happen if that happens? If the null hypothesis is true and we reject it, then I've got them backwards, by the way, guys. That's type 1. So let's talk about type 1. If we reject a true null hypothesis, then what we're doing is we're not going to end up using the drug, even though it doesn't go above 20. Does that make sense? See, the type 1 error, is if we rejected a null hypothesis that was true. And if the null hypothesis was true in this case, then that would say that the drug is, it doesn't go above 20, and we reject it, then we're going to say, uh-oh, we got blood pressure that's bigger than 20, no medicine, okay? No medicine in type 1. So what's going to happen? Well, we're not going to give this medicine that could possibly help these people. Type 2 error would be the other way around. Type 2 error is that we would fail to reject the null hypothesis where it actually is false, meaning that what's really happening is that the blood pressure is increasing. So if the blood pressure is increasing and we're giving them the medicine, okay, we're giving medicine. I can't even spell medicine, guys. That can be dangerous, right? We could be giving them medicine that could be bringing up their blood pressure and possibly kill them. Well, I tell you, I think this one is more serious in context than this one. In a type 1, sure, we might not help those people that could get help, but we're not killing them. That's what we're doing here, right? That's dangerous. We might end up being in trouble there. After this experiment produced inconclusive results, the researchers decided to test the drug again with another group of patients. Describe 2 changes they can make in their experiment to increase the power of the test. So how do we increase power? We increase power by increasing the alpha level, right? So we could increase the alpha level. We can also increase the sample size. Well, let's just kind of think about this, guys. If we increase the sample size, then we have to put more people through this test. And putting more people through this test might be a financial difficulty, right? We might not be able to afford to do all of this research with all these people, right? So that might, plus if we're wrong, man, we got a lot more people that could possibly be in danger, right? So we could possibly endanger more people. It could be costly and difficult. By increasing our alpha, though, we could be rejecting the medication that's actually okay. So we would be doing that more often. That's the disadvantage of both. Okay, let's do the last one here. An insurance company hopes to save money on repairs to autos involved in accidents. 2 body shops in town seem to do most of the repairs, and the company wonders whether one of them is generally cheaper than the other. From the files of payments made during the past year, they select a random sample of 10 bills they paid at each repair shop. The data are shown in the table. Indicate what inference procedure you would use to see if there's a significant difference in the cost of repair done. So, I think that these 2 groups here are independent groups, right? The cars done at Bodies at Bach aren't done at Velleman's Auto Magic. So we're probably going to use a 2-sample t-test with independent samples. Right? Let's take a look, make sure that's right. Okay, t-test for difference of means. The samples are independent. So let's talk about the assumptions and conditions. We've got 4 that we need to deal with. The first one is random. I'll just write these out and we'll talk about them. 2, less than 10%. 3, independent groups. And 4, nearly normal. Okay, so what you're going to do is, were they chosen random? Yes, it says random sample of 10 bills were paid. Less than 10%, 10 bills are less than 10% of all the bills that are paid to each of these repair shops. There's no reason why we think that one car will be at both shops, so they are independent groups. Now here's the one you really have to check, nearly normal. Is it going to be nearly normal? Well, you have to put in the calculator and do a histogram, all right? When you do that, the Bach data are unimolar and roughly symmetric. So the bodies at Bach are going to be unimolar and symmetric, but Velleman's Auto Magic, when you do it out, is going to be skewed, right? So if these data right here are skewed, then it doesn't pass the nearly normal condition, which means we can't actually do the test. So this problem here says indicate whether you could proceed or not. We would say no, because Velleman's Auto Magic is too skewed. Remember, this has to be roughly symmetric and unimodal, but this guy, if you check in your calculator, is pretty skewed. All right. So it does not pass the nearly normal. Remember that if we're doing a 2-sample t-test, both samples have to pass the nearly normal model, nearly normal condition. Okay, that's it. That's all of them. I don't think I have any. Oops. I don't think there are any. Well, there's no questions in the comments area, so I don't know if you guys have any questions or even how to do that. I've never live streamed on YouTube before, so it said that I could. I don't know how to do that. If you guys got a little link there, you can enter in on the comments below, and then I can check the comments. I think that might work. So if you want to ask any questions, I have about 5 or 10 minutes left to answer any questions. So I won't just stare here, but I could. So I'll take a look to see if there are any comments, if I can figure out how to do that. Check my hair, check my do. Okay, let's see. Comments. So I see a comment that says, "Hey," with a smiley face by Possum Drool. Cool. So it looks like I can see some comments. So if you have any comments, let me know right now, and I will answer any questions that you might have about the test tomorrow, or if you have any questions about independent samples or dependent samples and inference on means. Live control room. And a couple things to remember too, guys, is that you just want to make sure that you just follow the same rules as when you did inference on proportions. The equations might be a little bit different, but the ideas are the same. Okay. And I don't know if YouTube recorded this session. I'll find out. Like I said, I've never live streamed anything, so we'll have to see. And if it did, then what I'll do is I'll post it on my website so you can see the discussion that I went over and all the stuff I went over tonight. Okay. Nothing in the comments. Seems like I am going to sign off in just a second. Thank you for joining me. Hopefully it worked out for you guys. Again, this was kind of like a test run, and I'll see if it works out. Then I can do some of these more in the future, especially as we get closer to the AP exam, because I know other people around the world, or at least the United States, are trying to figure out how to get ready for that AP stats test, and hopefully I won't be coughing and trying to get over from this crazy sickness, whatever I had, and I'll be a little bit more animated and have some more stuff to do. So let's see. I have no idea what that is. Just checking some settings here, guys. All right, well, if you have no questions, again, I don't see any questions on the comments. Or if it did come up and I don't see them. Oh, look at that. Here we go. Is the test tomorrow going to have one hypothesis test problem from each chapter? That's a good question. So the test tomorrow actually will not have really any hypothesis test questions that are not on inference on means. So as you saw in this one, we did a lot of stuff. You know, there was a couple. There was like one multiple choice question about proportions, and there was the matching that we did in class with knowing which test had proportions. But none of them will you actually have to do a hypothesis test. In fact, I don't actually think any of them you actually I don't think any of the problems you have to actually do a hypothesis test. It's more about questions about the hypothesis testing. Excuse me, understanding the p-value, understanding the confidence interval, what those mean, how to interpret it, all those types of things, and not actually running through the entire thing, entire hypothesis test. So like you saw in these problems, there wasn't any real hypothesis test that you had to do, but there were a lot of questions about them. There are very, very few on proportions, just kind of a couple to make sure that you kind of know what you're doing, and you remember that stuff. And then also the matching. that we did in class today is going to be on there too. So do you have to worry about proportions? I wouldn't say too much. Know how to know if it's going to be a proportion one and how to do a couple things, but you won't have to run a proportion hypothesis test. In fact, you won't even have to run a t-test. You just have to know how to explain the t-test and know the parts of it, assumptions and conditions like we did on the last one, and so forth. So I hope I answered your question. I figured out why I couldn't see the questions because I wasn't refreshing the page. So once I refreshed the page, I saw the question. I didn't leave. I answered the question, I think. Let me know in the comments if I did answer your question before I sign off in about 4 minutes here, 9:30. Thanks, Lucy, for sticking up to Merrick, sticking up for Merrick. Don't leave. Merrick has a question. Good. I'm glad you got it. Okay. Any last questions before I sign off? Think about it. Again, I'll be here for 4 minutes. Excuse me. My coughing. Jeez. I swear I'm getting better. I swear. That's weird. Will the test be all done in 1 day, or are you split into 2 days for free response and multiple choice? This is a smaller test. There are only 10 multiple choice, and I think 5 free response, and most of the free response are more writing. You won't have to do an actual long hypothesis test. So this one can be done in, well, I should say should be done in 1 class period. So I'm not splitting this one up because it's only half as long as the other test. Ashley actually asked me a good question. She said, so this is only on inference on means? And I said, pretty much yes. She says, well, we have one that's going to include everything. And I said, well, yeah, you will. That one's going to be longer. Will probably take 2 days. This one's just 1 day. And just so you know, the reason I did it this way with the live stream instead of the Google Hangout was because there was some problems with some people getting on the Google Hangout, and there was also some problems with people with it only having 10. And I figured the live stream allows me to have, pretty much infinite amount of people. It's not as good to talk to you. You can't talk to me easily. You have to type it in the comments. But I think it might be, hopefully this worked a little bit easier for people to be able to access it on YouTube. You can let me know later. I'll try different things, but I wanted to be able to get as many people as possible. Do we need to memorize the equations tomorrow? They will be provided. Only the ones that are on the formula sheet will be given to you. The one that I talked about earlier about the means, when you have the means in that you pull them, I'll give that to you if there's a problem like that on the test, which I think there might be, but I'll give it to you anyway, so you can just plug it in. Other than that, I don't think you need the formulas. If you really need, like, let's say the confidence interval formula or the T formula, you're gonna want to memorize those. So you're gonna want to memorize how to find the T formula, what the confidence interval stuff is for T distribution, because all I can give you is what's on the AP exam, and that's the AP formula sheet. So that's pretty much all you get. All right, guys, I am signing off. I'm tired. I got some other work to do. So hopefully this helped. If you guys have any questions or anybody else has any questions, come see me tomorrow at lunch after my mu alpha theta meeting, and I'll see what I can do. All right. So see you guys later.